Hi, my name is Paul Gavrikov. I'm a PhD student at the Institute for Machine Learning and Analytics at the Offenburg University in Germany, and today I'm going to present you our CVPR2024 paper, Can Biases in ImageNet Models Explain Generalization? So as you probably know, ImageNet models form specific perception biases that separate them from human vision. In our study, we take a look at three of them, specifically the shape texture bias, which says that humans really rely on shape information to recognize objects, and models prefer the texture information. The second bias we're looking at is the critical band, which says that humans actually use a much more narrow critical band in the spectral domain, which they're sensitive to, and models have a significantly wider one. The third bias we're looking at is the spectral bias, or a high frequency bias. So here we have an image which is divided into the low frequency component and the high frequency component, and models will recognize the bird rather well on the high frequency component alone, but not so much on the low frequency component, and for humans this will be quite the opposite. So a lot of previous studies actually suggested that when you fix these biases, you also improve generalization. But often what they did is they showed a correlation on one specific category of generalization, and we want to take a look at a more holistic picture. We benchmark 4 separate categories here. So one other caveat of previous studies is that they mix different architectures, and sometimes these models even were trained on different data. So this may, of course, be a confounder. So what we want to do is we want to do it in a more clean way. We take 48 models that we study these correlations on, but we make sure that all of them use the same architecture, which is ResNet 50, and all of them are trained on the same data, which is ImageNet 1K. The only thing we vary is the training method. So we're looking at different kind of augmentations. We're looking at adversarial training. We're looking at contrastive learning or improved training schedules, and see how that influences generalization. And we test generalization on 4 different categories. One is in distribution data, which is kind of similar to your training data, robustness data sets, which is your training data but slightly modified, conceptual changes, which probably don't really look like your training data anymore, and adversarial attacks. And overall, I can, of course, show you all the results that we have in our study, but the most important one is when you look at a single bias, that really cannot explain generalization. Even when we find correlations on one specific aspect of generalization, it doesn't really transfer to other categories at all. And sometimes there are even inverse trends. So for example, there might be a positive trend for clean data and a negative trend for adversarial robustness. Surprisingly, we also find that aligning does not really guarantee anything. Quite contrary, we have found cases where alignment hurts. So for example, the models that have the best ImageNet accuracy have the lowest shape bias or the highest texture bias. Similarly, the most robust models have an unreasonable amount of a high frequency bias. So they recognize information they probably shouldn't even recognize. So the takeaways of our study is if you do such an evaluation, you must ablate external data and inductive biases. Otherwise, you may under or over-report things. The second thing is if you're just optimizing one specific perception biases during training, this will unlikely help your generalization in a holistic way. But if you have one specific optimization goal, so for example, you're trying to improve one specific type of corruption, or you're looking at one specific training mode, like for example just adversarial training, then a specific bias can have a nice correlation and probably also a causal connection to your task. And even though that I would not recommend to just fix a bias to improve generalization, I want to say that there are still cases where it's reasonable to do so. One of them is interpretability or alignment research, of course. And if you're a VIT fan, don't worry, we also have results on VITs in the appendix. And by that, I want to thank you for your attention. Please visit our poster session if you're at CVPR and take a look at our paper, or scan the QR code on the right to get access to all our code and the entire model zoo. Thank you.